Everybody, this is Mrs. Dinkelman, and these are the notes for 8.1, which really talks about two things. One is the average value of a function, and the other is, they're calling it accumulation of rate functions, but basically, how do we analyze applications problems that have to do with antiderivatives, etc. So first of all, with the average value, what we're really trying to find is, think about this curve, and again, maybe even just the area under the curve. Could we draw a rectangle that has the same area under the curve from A to B? So Gary's trying to get us to draw a horizontal line segment that would kind of give us the average height, or where would we have to draw the height so that the area would be the same as the blue area? So maybe in there somewhere. I think it needs to be a little taller. So maybe in like here somewhere. Maybe a little lower than that. But what we're, again, trying to find is there a rectangle? And how tall would it have to be so that the area under the blue would be the same as this area in the red, okay? The way we would find the area of that rectangle would be we'd have to know what this width is, and to find that we would just subtract. So like this was at 2 and that was at 7, we would know it was 5. So that's really a B minus A if we're using the symbols. And then we know that the area under the curve is really just the integral. So what he's trying to get us to see here is we're getting the area under the curve to equal the area of the rectangle. So I'll just write that here. This is curve, this is rectangle. And then we're going to basically solve for height here. So that average height, trying to decide how tall I'm supposed to draw that rectangle, is going to be the integral from A to B, and then divided by B minus A. So that's really the formula that we need, and you'll see that here with this information that Gary has for us. I tend to think of it this way for some reason. Instead of just a big divide problem, I do the 1 over B minus A. They're the same thing, it's just that that's the way my brain kind of thinks of it. So as we're setting these up, so for instance number 4, we're going to go 1 over 2 minus 0, integral from 0 to 2 of the function. And then it's just a matter of calculating. So yes, we have that 1/2 out there, and then our antiderivative. And then we're going to evaluate just like we would with a normal integral. Luckily in this one, I see the 0, so I always like it when that happens because it's a little easier. So 16 over 4, and then 4 divided by 2. So I think we just get 1 for that. So we're saying that the average height is at 1, basically, if we were trying to draw that one. It's a little interesting to think about that one that dips below the axis a little bit. Okay, and then it says use the calculator to find that value. So all we're really doing is trying to figure out how we get x cubed minus x to equal 1. The reason they're giving us a calculator is because it's kind of not a nice one to look at, but I'll let you solve that. Or we can, a couple ways to solve that. We could use the solve feature, or in y1, we could put x cubed minus x minus 1 and try to find the 0 of the function. So I'll let you kind of do that one. All right, so then we've interpreted, like it says here in 4.1, we've interpreted rates, but we haven't really done that when we're taking the antiderivative. So they're just making sure that we know what we're doing as we do that. So the graph on the right is a rate. So it says it's the rate of rainfall. That's what the y-coordinate is. And we can look there. I always kind of hone in on the units. That way that can help me kind of write the sentence sometimes. We talked about that in 4.1 when we did it as well. So 6 says, first of all, we're going to explain what point A is. So we're looking there. And there's a couple things that I just want to mention that we have. So we're talking about at time equals 3 hours. And then, let's see, that's a 1 for our A there, and that's in inches per hour. And it actually kind of describes it, rate of rainfall. And so when we're trying to write this complete sentence, we're going to make sure that we include both of those things. So that 3 hours in, and maybe we should look. An hours from midnight. So we might as well say at 3 a.m. And I'm gonna steal their words, the rate of rainfall Didn't need to capitalize that, but I did. Is 1 inch per hour. Again, sometimes they ask us questions like describe in context, so that's kind of what that means. Okay, what's the slope of the graph between B and C? Be careful about units here. So it's really down 1 over 1. So the slope is -1, and I'm already going to think about what that would be. That'd be inches per hour. Okay, the y over the x. So again, the change in y over the change in x is our slope. And just remember the units for the y are inches per hour, and the units for the x are hours. So that's why we get to do inches per hour or inches per hour squared. Okay, so write a complete sentence. There's a couple things. We want to talk about when, just like we did on number 6 there. So it's between the hours of 4 a.m. and 5 a.m. Okay, so that describes the when. And what's happening is our rate is negative. So our rate is actually decreasing because we get a negative. So we want to say something about that. So like the rate at which the rate of rainfall maybe, or rate of rainfall is decreasing. I like to sneak in that either increasing or decreasing word based on the fact that it's either a positive or negative from what I found in number 7, is decreasing at a rate, or I already said rate, decreasing, I guess I can say at a rate. I don't know how else I was going to say that. And we'll make sure again that we include the units. And if you do inches per hour squared, that's totally fine. Okay, number 9, integral from 3 to 5. So Gary sort of shaded that for me. I kind of want to split it into a triangle and a rectangle. So that rectangle is really a 1 by 1. Careful about that unit. And then 1 by 1 divided by 2. So that's equal to 3 halves. Now let's think about this. Remember, the integral is really finding the antiderivative. So if the derivative is inches per hour, then the antiderivative must be in inches, because derivatives are technically rates, basically. Okay. All right, so write a complete sentence for that one. So this is between 3 and 5. And again, we kind of already have that, so we know that this is inches, and that's how much it rained, basically. So it rained a total of 1.5 inches. One and 1/2. So again, a couple things in there. Make sure you say when, that 3 to 5, and include the unit in there. Approximate the value of 0 to 6, the integral, using geometric regions. So we kind of already have the 3 to 5. 6 doesn't have any. It looks like it must not have rained. So we just need to figure out basically what's happening from 0 to 3. So I think maybe I'll just use a triangle right there. We could do a couple of rectangles or something like that. So I'm going to go, this is a 3 by 1 divided by 2. And then we already had the 3 halves. Okay, so maybe I should write out kind of what we're doing here. Basically, I'm estimating what the integral is from 0 to 3. And let's see, what did they name this function? I was going to call it f of x, but I better not. I guess it's just r of t. R of t, that's the one I think is, again, that's that triangle. We already found from 3 to 5. That's what we did in, let's see, that was number 9. And then, like I said earlier, it looked like from 5 to 6, there was nothing there. So that was the 0. Okay, so I'm going to say it's 3 halves. Again, they're integral, so that's inches. And this is an approximate, right? So we probably want to say something about approximate, and let's see when. This is during the 6 hours, or from midnight to 6 a.m. or something like that. So from midnight to 6 a.m. I'm going to sneak in that word approximately. Oops, that's not 3 halves, that's actually 6 halves. Hopefully somebody was going to fix my work there, so that should be 3 inches. Approximately 3 inches of rain fell. So again, these are just kind of they're application problems where there's a context like rainfall or snowfall or something like that, and we're just trying to describe, I mean, we're sort of being mathy in there, but we don't want to just say the derivative or the integral because the people don't really know what that means necessarily. So we want to talk about what the integral would mean, which is how much rain has fallen or the total rain or something like that. Okay, you can go ahead and get started on the assignment. I don't believe there's any to skip. Let me just run through and just take a quick peek. Mostly the ones that we usually skip are those integrals if he gives us any of those. Okay, I don't think there's anything, so go ahead and get started on the assignment.